Okay, good morning, students. So we will start with the spectrum of sinusoidal amplitude modulation wave. So this is amplitude modulation. We'll continue with this. So we have spectrum of sinusoidal AM signal. So first of all, you have modulating signal, and that usually can be any type of signal because that's called an information signal. So you have modulating signal. This one, let this be your modulating signal. This is T and this is M of T. Now from modulating signal, you have one signal that's called carrier signal, right? Okay, so let this be carrier signal. It's sinusoidal. T. This is T and this is your C of T. Okay, and then since after modulation you will get two side bands in the form of this, so you have the signal like this. Wait a minute, I will draw the graph properly. Okay, this will be your AC. AC is your amplitude of carrier AC. This is your minus AC. That means it's peak to peak amplitude is minus AC to AC, right? So this will be your minus AC. Done. So this one will be your AC plus AM, where AM is the maximum amplitude of your modulating signal. That's also called baseband signal. So this one will be your AC minus AM. So your signal will start like this from here. Similarly, this is minus AC. This will be minus of AC minus AM. Then this one will be minus of AC plus AM. Okay, so finally you have signal will be like this. Okay, so your signal, this in between this envelope, you will be having your carrier signal. Okay, so this will be your envelope. This will be your top envelope of AM. This will be your bottom envelope. Bottom envelope. So are you getting me? What ultimately you will get? This is your baseband signal. This will be carrier. This carrier will be modulated by, you will modulate this signal in accordance with your baseband signal. That means C of T will change from this to this. And this is the final signal that's ready for the transmission, right? This is your SAMT, modulated signal ready for the transmission. Are you getting me? Everybody getting me? Hello?
Yes, sir. Yes, sir.
Okay. Now, you just have one thing. I will derive certain points here because that's very important. From the above graph, you can conclude that 2 AM is V maximum voltage, V max minus V min, where V max is this voltage. This is V max, total voltage. This one from here to here, this will be your V max, right? This will be your V max voltage. And this will be your V min voltage, this one, V minimum voltage. So finally, you will get twice AM will be equal to V max minus V min. So from this, you can conclude AM is always equal to V max minus V min divided by 2. Similarly, you will get AC is equal to V max minus AM, V max minus AM. So AC is equal to V max minus AM. You can conclude this. So V max is from here to here. So if you will subtract AM from this V max, then you will get AC. That's this from. So that's what I have wrote here, that AC is equal to V max minus V AM minus AM. So finally, you can put the value of AC equal to V max minus AM, this first equation. Second, put the value of first equation in second, you will get V max minus V min divided by 2. Done? Any confusion till now? Hello?
No, sir. No,
Okay.
sir.
Okay. So just solve this equation. So you will get twice V max minus V max plus V min divided by 2, right? Then this, further on simplifying, you will get AC is equal to V max plus V min divided by 2. So this is your AC value. Similarly, you have already done with this. AM is equal to V max minus V min divided by 2. So let this be equation A, let this be equation B. Then on dividing B by A, what you will get? Because B by A is AM divided by EC, and that's nothing but your modulation index. This is your modulation index. It's also denoted by mu sometimes. So this is your modulation index. And this is equal to V max minus V min divided by V max plus V min. So you can see your modulation index is finally equal V max minus V minimum divided by V max plus V minimum. This is your modulation index MA, also denoted by sometimes mu, can denote it mu. All right. So if the value of ME is 1, you can say this is 100% modulated wave. 1, or you can say 100%. So this is called, you can get percentage modulation on multiplying by 100. So this is your 100% modulated wave. So modulation index, it gives the insight, or you can say it gives the depth to which the carrier signal is modulated. We'll see its values, it may vary. See, its range is always from 0 to 1, because this will be always smaller value, Vmax minus Vmin, and Vmax plus Vmin, it will be always greater value. So its value range is from 0 to 1. Done. And what does this gives us? It gives the insight, it gives the depth to which the carrier signal is modulated, to which the carrier signal is modulated, and obviously carrier signal is modulated in accordance with your baseband signal, or in accordance with your message signal, right? Suppose one of the value I will take here. Anybody having any confusion till now? Hello, anybody having any confusion? Please tell me.
No, sir.
Okay, so you have MA. If this should be always for the purpose that envelope should be preserved, means for that message should be transmitted clearly and envelope should be preserved. For that, MA should be modulation index should be always less than or equal to 1. That means it should be always less than or equal to 100%. That is because MA is equal to AM divided by AC. It should be always less than or equal to 1. You can say AM should be always less than or equal to AC. That means amplitude of carrier should be always greater or equal to AM. That means amplitude of message signal should be always less than or equal to amplitude of maximum amplitude. I'm talking about maximum amplitude of carrier signal. So its range is always equal to from 0 to 1. Now, sometimes if MA is greater than 1, then you have this is called as overmodulation, and that leads to the interference problem and other problems. In this case, your envelope is not preserved. Your envelope is not preserved, and message signal will get distorted, is not preserved, and you will have distortion. So, suppose you have this. In case of undermodulation, you can say, or critical modulation. Undermodulation is when your MA value is less than 1. If MA is equal to 1, that means modulation index is 1 or 100% or less than 100%. This is called undermodulation, and this is called critical modulation. And in case of overmodulation, we have value of MA should be always greater than 1, or you can say greater than 100%. Greater than 1 or greater than 100%. Now, you just, I will draw the graph of this. First of all, under modulation and critical modulation, these two. That means MA is less than or equal to 1. What will be the graph look like? So you have this is your suppose V of t voltage, then this will be your envelope, right? So this will be your carrier in between these two. This is your sinusoid in between these two envelopes, right? So
Yes, sir.
this the maximum value. This is your AC 1 plus MA, right? So then you have this value here. This will be your AC value, carrier value. And the minimum value here, that's this. This is your AC 1 minus MA value. And this comes under modulation when MA value is less than 1. When MA value is less than 1, then this type of modulation will happen. In this case, there is no distortion, nothing will happen. And you don't have any kind of non-linear distortion here. And in this way, waveform is preserved. You can say your waveform is preserved whenever you have amplitude, this modulation index less than equal to 1 or less than 100%. Now, in case of over-modulation, what will happen? Critical modulation, you just do yourself, draw the graph like this, and it will just touch this. It will touch this. This value will touch this one. Okay. So I draw the graph of over-modulated signal. So in case of over-modulation, you have MA greater than 1. This is called over-modulation. And you will see there is one typical problem that's called as nonlinear distortion. That's also called envelope distortion. That problem persists in this, and that problem is envelope distortion. We will see that. What is that? Envelope distortion, or you will say, or that's called a nonlinear distortion. Nonlinear distortion, right? So you just draw the graph of this. You will see that your yes one like that. Similarly, in the negative half cycle, it will be like this. That means they're crossing each other. The whole envelope is not above the zero, this above the x-axis, it's between these two. That means it's in positive half as well as in negative half. This is the positive half and this one is the negative half. Similarly, this one is positive half and this one is negative. This is the positive of this is negative, this positive, negative. And because of this crossover, distortion will occur. And this type of distortion is called envelope distortion or nonlinear distortion. You just draw the carrier in between these two, you will have like this. You got it? So this problem here and here is called as envelope. That means your information that's preserved in the envelope is distorted. That's the reason you're calling this envelope distortion or nonlinear distortion. Envelope distortion or nonlinear distortion. And this problem occurs whenever your modulation index is greater than 100% or greater than 1. That means if you will put the value of MA equal to AM divided by AC is greater than 1, what does that mean? Your AM maximum amplitude of modulating signal is always greater than the maximum amplitude of your carrier signal. And that situation is not desired. It will lead to you envelope distortion. That means information will not be preserved by the envelope and you will have a problem that's called nonlinear distortion or envelope distortion. Done? Okay.
Yes, sir.
Now we will study the power relation in AM. So next topic is your power, rather normalized power relation in AM wave. I will, before going for the power, I will rewrite the standard form of amplitude modulated wave that's equal to AC cos of twice pi fct, right? Then you have ECMA by 2. Please mute your mic. Then cos of twice pi FC plus FMT. Then you have plus ECMA by 2 cos of twice pi FC minus FM. Right? So this is your standard form of EM in terms of modulation index. Now, this one is your carrier signal. That means in the modulated wave, you will get carrier. And this is just a wastage of power because we don't need carrier. We need the message signal that's in terms of this envelope, this and this one. So then you have one sideband that's called upper sideband. Upper sideband you will get, and then you have lower sideband. So total power of your modulated signal will be always equal to carrier power because you have one carrier component here, and then you have one power of upper sideband, then you have power of lower sideband. This will be the total power will be equal to the PC plus PUSB and PLSB. Now, can anybody tell me what will be the value of this? What will the power of this? Tell me. Whenever you have sinusoidal this signal AC cos of twice pi or sine of omega t power, and this is suppose x of t equal to this. So power will be always equal to AC by root 2 ka whole square. And AC by root 2 is its RMS value square. So power will be AC by 2 normalized power. If I will take R equal to 1, they will be divided by R, and R you will take equal to 1. Right? Because power is always equal to voltage square divided by R. R is resistance. If you will put the value of R equal to 1, then you will get power equal to voltage square. And this is called as normalization. Normalization or normalized power value, you can say, because you have put the value of resistance equal to 1. So same is the case I'm applying here, that power will be equal to AC by root 2 ka whole square, and R will be obviously there 1 by R, and R value you can put 1, then you will have power equal to AC square by 2. This is for carrier signal. Can anybody tell me what will the value of upper side band, power of upper side band from this? Because here amplitude will be now AC into MA divided by 2. This will be the whole amplitude of this upper side band. Now tell me, can anybody tell me? No? So you have PC value equal to AC square by 2. Then you have upper side band. It will be equal to AC MA square 2 into 2. This is already 2. Then you divide it again by 2. Right? So you will get AC ACMA divided by 2 into 2. So ultimate value, your upper side, total upper side band value will be equal to ACMA square divided by 4. Done. So final value which you can put in the equation, above equation, you can say that PT is always equal to AC square divided by 2 plus AC square MA square divided by 4, because this is total upper sideband power, total sideband power. So finally PT is equal to, you can put AC square by 2 common, then you will get 1 plus ma square divided by, tell me, this will be 2. So this is total power. Can I say this is nothing but your PC carrier power? So this is PC into, okay, I have a few minutes left. Let's wind up this. Okay, so this will be 1 plus me square divided by 2. So this is the power relation in case of amplitude modulated wave or amplitude modulation. You can say, finally, you can conclude that PC carrier power is independent of mu or MA, that's modulation index, but your sideband power, they are dependent on MA. So depending upon the variation of MA, as you increase MA, your sideband power increase. But PC will have no effect on MA. That means modulation index, as you increase, carrier power will remain constant. But since if you increase MA, it will subsequently increase sideband power. That's one relation you remember. Suppose one thing I will just conclude before going for this. Okay, suppose if you will put the MA value equal to 0, that means no modulation case. Put this value in the above equation. Put this value in the equation A. Tell me the value. PT will be then equal to, anybody? PC 1 plus 0 square divided by 2. 0 divided by 2. What is the value? PC 1 plus 0. So this will be PC. So total power will be equal to carrier power. And that means there is no modulation because you are transmitting the carrier, but we need the transmission of your message signal M of t. So there's no modulation in case of this. So you just put different values, MA, put 1.5, then 1, then 1.5, and tell me the different values of power. Okay, so we will stop here. Tomorrow we will continue with the power relations and we will do few numericals on the same. Anybody having any confusion, please tell.